All right. So, hi everyone. Today we'll be presenting the histograms as objects tool for efficient analysis and interactivity talk. Just in case you want to run the talk along, there is a run on binder button in the agenda, and we have the GitHub repository too. So if you go to the repository, you have the badge there too, if you want to launch the binder. And as you can see, the binder is loading here, but I'll use a local copy for now. So and just get started. Okay, so hi, today we'll be presenting histograms as objects, and we'll see why these tools are so important to high energy physics. We'll be talking about a couple of libraries and a new one. And the co-authors for this talk are me, Aman, Dr. Hans, Henry, and Jay. And I and Jay would be doing the talking today. So there is a binder and a Zenodo DOI in case you want to access that. We have the quick links on the top where you can access all the relevant material for the talk. And in case you have any questions, please feel free to put them on Slido. Now, Jay will get us started with the introduction of the talk.
All right, thanks, Aman. We'll start with the very fundamentals. Now, if you go by the standard definitions, histograms are group frequency distribution-based representation of occurrence of numerical data points. But what that really means is that when you group numerical data into frequency-based distribution and then visualize it, you get histograms. So that's histograms for you in general. Now, histograms comprise of axes where the horizontal or x-axis is usually made up of the classes where you distribute the data, and the vertical y-axis where you group the data, where you fill the data. So as you can see on the screen, we have numerical random data, and the classes are basically the numerical values, and the y-axis is the instances of those numbers. So that's histograms in general. Now, if we quickly, so here what we're doing is trying to import the standard libraries and then generating random numbers. And then we are creating a data object that has those random numbers. And then we are creating a Hist object that has just a single regular axis with integer data type. And we're filling that with the data, random data we created. And when we try and visualize it, this is what we get. And we can also run that in matplotlib, which is what you see here. And we can also slice that. So if you want to see slice, and we can transform it. So that's what we have here. And then there's also a NumPy API. If you can uncomment that, yeah. And then this is what we get. So this is how you create histograms in general. Now with Scikit-HEP, we have if you want to get into histogramming, we have two main libraries for that. The first one is boost-histogram, and boost-histogram is basically a Python binding for the boost-histogram C++ library, which is one of the fastest in the field. And Hist is a friendly histogram library that basically extends the functionalities of boost-histogram. We have name access, a lot of shortcuts that comply with UHI, and well, much more. So if we, and then there are a few other memos as well, like UHI, MPL, HEP, histoprint, and task histogram. But today we'll be focusing on boost-histogram and Hist, and at the end, uproot-browser as well. Now, with the Hist object, now it comprises of two basic aspects. The first one is the axis object, which is like the actual axis, right? What an axis object defines is how the data is going to be stored. And when we talk about storage, it's more about what type of data is going to be stored. So these two aspects are really key to a Hist object, which is the extended library of boost-histogram. And with Hist, we have regular variable integer category access. If you can scroll down, yeah. And then with storage, we have simple storages that include double, unlimited, integer, and atomic integer. And then with accumulator storages, weight, mean, and weighted mean. Now, if you see in the diagram, You can see the regular axis, which is, well, regular. We have variable that varies. We have integer, then integer category, where we have a group of integers, which are category-based integers, and then we have axis based on that. And then we have a string category, where it's just a character version of integer, where we have specific strings that represent the axis. And then there are a lot of parameters you can pass to Hist. Some of them are underflow and overflow. You can turn them on, and then they will collect, those bins will collect the data when it underflows or overflows. You can also have a circular axis where, well, there are a lot of applications where we need circular axis, so we have that as well. And you can also have growth as true, and the size of the axis will keep changing. It will grow as per the requirements. If we move forward. Now, defining a histogram with Hist. If you want to do that in the classic manner, we create a Hist object and then pass in the axis. Here you can see that we have two of them, which are regular. We have arguments 50 from -5 to 5, and then as this is an accelerated functionality of boost-histogram, we can even name them and give them labels. So we have given S and W here, and then we provide the storage, and then once the object is created, we can just print it. And then if you want to do a quick construct, we don't need to write the whole thing. We can just do .rec, and then that will be equal to histograms axis regular. And even we don't even need to provide the storage is equal to parameter. What we can just do is put the weight in here, and then it constructs that. And if we run that, it gives us the same output. And then if we try and do that with boost-histogram, what we have to do is call boost-histogram and then open the histogram object, and then again pass the axes. It's again regular, two regular axes. The first one, as you can see, is circular because we have passed that parameter Boolean value. And then there's a third one as well, which is variable. Now, when you print that, you get a similar output. Now, this is creating and creating the histogram. What about filling it? So if you remember the random data that we generated, we use that here, and then we pass the current values, and then we fill that with h.fill, the fill function, and then we provide the values. And if we try and plot that, we can again use matplotlib, and this is what we get. Now,
thanks, Jay.
Aman, if you want to go ahead.
Sure. I'll continue from here. So as Jay told us about how we make a histogram, define it, and then fill it, and we can also pass it via MPL-HEP, which uses matplotlib to plot the functions. Now here what we see is basically a 2D histogram with the S and W axes. Now another feature that we have here is that we can project this to one of the axes. Say I use the S axis, and then we plot it. Oops.
Yeah.
So now we see that we have a 1D plot, and this would be the same since the data is same in the S and W axis. We can project it to make it a 1D histogram. Now Hist has a feature called hist-rep, which basically has customized reps, and they display in the Jupyter notebook. So what you'll observe here is when we project this, we get this representation within the Jupyter notebook. And what you'll see is that we didn't call the plot here, or we're not calling any library. This is basically inline HTML, which helps us get an idea of what the histogram looks like. So basically, when we do this, we get the 1D histogram, and say we do not plot the whole histogram, but we still can get a representation on the Jupyter notebook. Now, what we can also do here is Hist has functionality to plot this in various ways. So say we do a .show function. What it'll do is it'll print it via histoprint. And this is again, this is using ASCII code to print it to the output. And similarly, say we do an h.plot, we'll get the plot that we got earlier, which is a 2D histogram, and this is being done by matplotlib. Now, besides the rep, we can use plot and show, as which I showed above. Now, what an issue that arose with all these histogramming libraries was that we had multiple producers and multiple consumers, but we did not have anything to tie them up. So UHI was developed in boost-histogram, and then UHI Plus was adapted to Hist, which basically extends boost-histogram's UHI and provides HEP users with handy accessing shortcodes. So it's basically a protocol which allows the libraries to interact, and say we want to find the centroid element of the 2D of a 2D histogram. So first we'll define a histogram. I'll just move this to the next cell and say we have a histogram which looks like this. Now, if you want to find the centroid element here, what we do is we check it via both UHI and UHI plus, and we see that the outputs are same. So it's basically extending on boost histogram's UHI. Now here, the syntax that you might observe is that we are slicing and we're using the log keywords, which we'll get into later. Now, what is basically happening here is that we are looking at the locations on the location coordinates on the axes, and then we're defining them, and then we're saying that we want to get this exact location. So basically, when we do bh.loc, it goes to the 0th location, which is 0 on the axis on X and Y. And here we get the centroid element. Now, how this was made even quicker, a shortcut was made in Hist where you could use the J notation while you don't have to write the log keyword altogether. We'll try to do something with the PyHEP logo and see how this works. So here we have the PyHEP logo. We'll manipulate this as NumPy arrays, and we'll get some random numbers. Now what we're basically doing is we'll use probability here to make this data as a list of tracks. And then we'll use probability that if the tracks hit the image, then we'll get a true, otherwise it's false. So we define the probability, and then we say hits is equal to prob greater than p. Now, basically, we define the X and Y here, and this is where we are filling the new histogram. So we have an histogram object, which is basically this image. In fact, it's a cut image. It's not the whole image. And so we get a cropped image as a form of a histogram. And then we define a function. What we can also do is we can use directly the plot function, which would work in Hist. But here, what we're doing is we're manually defining a matplotlib function, which does the plotting for us. And when we call this, we see that we have the logo as a histogram. So this is a very high density histogram. We can rebin this to sort of have a coarser binning. And upon rebinning, you'd see that, say, we slice it and we use the rebin function. And this is how the rebin histogram looks. Now, say we want to zoom in on the Python logo at the center of PyHEP. So we see that it's around 0.4 to 0.8 on the x-axis and 0.2 to 0.6 on the y-axis. So say we look at the exact coordinates, what we do again, we do the slicing, but here we use the J notation. Now the J notation is basically going to that location on the axis and fetching that for us. And when we slice using those locations, we see that we obtain the Python logo. And this basically can be very useful for making cuts and getting one part of the data while rebinning it. Say you want a coarser or a finer binning number. Now, other interesting features that are there is one of his major feature is stacks that was developed recently. Now, stacks is basically, it holds multiple 1D histograms into a stack, and it requires matching axes to plot them. Now, when we plot it via MPL-HEP, we see this notation that we get. But the general stack notation that we want is basically the one which is filled inside, the one we're usually familiar with. So what we do is we pass the his type fill, and we also reverse it because it gets reversed for some reason. Now we get the stacks representation. Then we look at interpolation, which is being done via SciPy. So first we import the interpolate from SciPy. Then we define a evenly spaced numbers using NumPy, and then we define a hist object. So this is our Hist object. We have a wrapper here. We see that how the object looks like. Then we define our linear interp function, which basically tells us what kind of interpolation we're doing. And when we plot it, we see that we have a linear interpolation over the centers on the bins. We can also change the keyword here to cubic to see a cubic representation of the same. So another thing that we have with Hist and boost-histogram is now that they are supported on WebAssembly. So we can run them via PyHEP. I'll just do a small demo for that. I think we're a little short on time. I'll try to wrap up quickly.
Hey, Aman, we're not too bad given the next presentation spent 10 minutes long, but it was cancelled. So,
so I've got 5 to 10 minutes.
Yeah,
right?
you are okay. You're perfectly okay.
Thank you. Okay, so this is again all running on the machine itself rather than say on the binder. So this is this is the binder, but when we use Jupyter Lite, here we make the imports. Then let's install Hist. It's being slow. It's probably my machine. Okay, yeah. Now we have the import. We import Jupyter and then install Hist. Now we see that we can post Hist here. So that works. Now we'll just try to do a basic object, say import numpy as np. We have numpy built in. Then let's define a range from earlier. So say we define some numbers, and then we say h1 equal to hist. And this is basically we're giving the bin number and the coordinates for the x-axis. Then we say it's int 64, and then we fill it with the data. So okay. Wait. Oops. Okay, so we have the histogram defined. Now we can get the representation. We see that it's working on WebAssembly, and we can also do say h1.show here. That will basically pass it by histoprint, and we get the ASCII representation. And as we saw, we can slice it using the locations, say -4j to 4j. And that gives us a particular area of the histogram. So that's how Hist works on Hist and boost-histogram work on WebAssembly. Now getting back to our main notebook. So okay, I think yeah, that's about histograms. Now we have a new library to present today, which is uproot-browser. And I'll go over it a little. So again, the links are on the top if you want to access them. And uproot-browser is basically a new development that has been inspired by the root object browser. So let's first of all do some manipulations with uproot and see what's all about. So say we have a root file and we import it from the Scikit-HEP test data, and we use the uproot event.root. So we open that file. We define that file, we open that, and let's check the keys. So when we do file.keys, it shows us what are the keys present inside the file. So say we have a process ID, we have htime, hstat, which are basically histograms, and T is the tree that we have. So we verify that. We see here that, yeah, there is this. This is an unknown object probably. Then we have TH1F, which is basically a histogram in uproot, and then we have the T tree. So what we do is we say we want to check what is hstat. We put it to h, and then when we execute h, we see this. Now we can pass this h to hist, and we can plot it. So say we get this plot, and this is basically we took that hstat file, hstat histogram from the root file, and we passed it to hist and plotted it. So this is the content of the histograms, is the plot that we get. And similarly, say we want to see the tree. So this is basically the tree that is present in the event uproot file. So we can see that, like, this is again a lot of information, and this is the common way that we're used to analyzing any root file. But now what we have is a new way. And what if we could perform all of this with the help of a user interface? So that's where uproot-browser comes in. Now, uproot-browser is basically a plain-text-based command line library in which we can use the command line to interact with the root file. And it takes its inspiration from the root object browser. But as we see, I think the root object browser has moved to a web browser-based browser right now, but this is completely inside the terminal. So it has a few features now, right now, which is basically, again, a command line interface that we get to access via click. And it has browse, it has plot, it has tree, and we'll go to a demo to see that. I'll probably not run the demo in the Jupyter node, in the Jupyter Labs terminal, because it sometimes glitches. I'll just quickly share my local terminal. So yeah, so we have the terminal here, and we basically access the uproot browser commands. So first of all, we see what is there. So we do a -h, we get the help menu, which tells us all about the commands that are there and how to access about it. So say we look at the same object. Earlier, we looked at hstat, and so we say uproot browser. Then to look at hstat, we say we want to plot it. We go plot, and then we give the data. So that is where. Yep, that is the uproot event. So after accessing the uproot event file, this is basically how you access any directory in the system. We use colons to go further inside the file. So we say hstat, and when we execute that, we have the plot there on the terminal itself. So what's happening here is basically this is using plain-text to plot everything on the terminal. And say we do this again, but this time we want to see the tree. So instead of the plot command, we say uproot browser tree. We go to our object and we say T. So this gives us a beautiful tree with icons and with everything according to the different types of the data. So here we get the tree on the terminal itself. Now, these are basically the building blocks of uproot browser. But what is most exciting about this is that we can get a complete new user interface for everything. So we say browse, which basically ties these commands. And now we just say the file that we want to browse. So we go here. And when we do this, we're inside the GUI interface. So there is a text user interface. Basically, what this does is it has a clickable interface. And say we can switch the toggle bar and we can access the tree. So when I click on T, we have a scrollable interface here which shows us the tree. And this same thing we were doing with uproot, we had to give some commands and we were seeing all the information there. But here the information is presented in a different manner and for say a quicker access of things. So for example, we want to try to plot hstat again. We just click on it and we see in this window, we get the plot here. Then we can also toggle the sidebar, which automatically changes the size of plot and adjusts it accordingly. There are a few objects that uproot browser does not recognize as yet. So it's in very initial stages yet. And there is a new, so everything here is based on textual, and textual is basically transferring to a CSS CSS based library now. So we're waiting for that, but we might switch to the development version of that on our development branch. But this is basically what it does now. Now, what we also have is collapsing trees, collapsing, we have the hover functionality, it shows different colors. Then we can plot the different objects just by clicking on them. And then what we can also do is we can see how exactly to get this via uproot. So say we want to know how we access the edge stat. We do a quit with dump, which can also be done by the shortcut key D on the keyboard. And when we do this, we see that we have this, we have these lines of code which tells us exactly how you access that particular file. So that's how uproot-browser functions. And I think, yeah, that's the end of our demo. Thank you. Thanks so much.
Thanks very much, Aman and Jay. So I don't know if I actually posted a comment just so that you can explain a bit further, because I had the impression, I had the feeling that this may have been a bit tough for some newcomers, just because you were talking about different packages, not explaining how they actually interact together. And talking about uproot, by the way, if you want to know and you don't know much about uproot, that after the break we will actually have a presentation on uproot and awkward array, which we can give you much more detail about this. Where here you in a few places we're just using those packages to open the root files, which are often formats to then show features. So maybe you want to, maybe you can try to go through that first question. Maybe have a brief comment on those packages they have mentioned, Hist, Histoprint, and so on.
Yeah. So, okay. So basically what is happening here, so if we see an overview of how these packages work together. So first of all, we have the boost-histogram library, which is PyBind 11 and the boost C++ library, which gives us functionality via C++ and Python. And it gives us access to all the histogramming prowess that we have in a very high speed manner. Now, what Hist does is Hist comes in and Hist adds features to it, such as, say, the .j notation, or say the name and the axis notation. It adds metadata, it adds richness. So it's basically Hist is a front end for the boost histogram. And in Hist, we have access to histoprint, which is another library. And that helps us, say, plot everything on the terminal or on the Jupyter notebook itself via using a sky. So what Hist does is, again, it uses a lot of packages. So we're not trying to reinvent the wheel. So it's not, say, it does not have an inherent plotter. What it does is it uses other libraries which are already present. So we have math.lib, we have MPL-HEP, which is, again, based on math.lib. We have histoprint. So we use all these libraries to basically parse our Hist object, and that's how we print. Now, another thing that we moved to was uproot and uproot-browser. Now, uproot is basically an IO library for accessing root objects. And like we have root, the whole library root, we have the Scikit-HEP. It's not an alternative, so to say. It's basically an IO library. So root is a full-fledged library, but uproot, I don't think uproot offers that feature. I'm not sure, though. Please feel free to correct me. Anyway, so uproot is basically what we use to interact with root files in the Scikit-HEP ecosystem. And what uproot-browser does is it makes it even easier via TUI. So in uproot, you would have to type commands and you would have to, say, access particular things. But say we want a quick overview of the file itself, and we just want to see what's present inside, or want to see what is this tree or what is this plot. So that's where uproot-browser comes in, and it offers a terminal-based interface. So I hope that helps with the explanation. I'm sorry that I skipped over a lot of the basics. So, yeah.
That's all right. That's why I made the comment, because I can realize how difficult it can be sometimes.
Yeah.
But that's fine. All right. You had a few other questions. Maybe you answer the first one, and then we'll move the rest to the discussion to not eat too much of the break that is needed by everybody, of course.
Yeah. The rest of the questions we can answer on Slack. So I'll just pick this. Can uproot-browser use print key bindings? So uproot-browser does not have Vim key bindings yet. And I mean, it does have default up and down binding, which is again not very very intentionally designed. Since it's based on textual is providing us with that interface. So that has been a point of conversation in the past, but yeah, I think the primary motive there is to develop not like standard key bindings first, say you can access everything via the keyboard, and then maybe we can move on to the Vim key bindings too. So thanks a lot, everyone, and see you later.